So good morning for who is here and for who is online. So we will start our first day of training sessions. And today I will start with the in Python. So, and we will start using our virtual environment, and we will use like some of the Jupyter notebooks that we prepared. And in this session specifically, I will explain about the environment and like what Python libraries we will use, and in the other sessions we will like explain how we are producing the data sets in the context of the project. So before I start, I would like to introduce myself. So my name is Leandro Parente. My background is in computer science, and I started work with GIS data like 10 years ago, more than 10 years ago. And in the beginning, I worked more, I did work more with like web GIS development. So I used all these platforms that we heard about to put the data available, like GeoServer, Map Server. And so I started programming with Java, and later I moved to JavaScript. And I did my master's degree and my PhD in environmental science. And when I started, I moved. So, and in this area, I worked with like and on the end of my PhD, I used some of deep learn classification like UNet, and my PhD was mainly produce a pasture map for the Brazil. So I'm from Brazil, so I did this work there, and I used like Landsat data to classify the whole Landsat archive and produce annual maps for the pasture lands. So, and I did it in Google Earth Engine. So I will talk limitations and what is our current approach to apply like spatial and spatiotemporal machine learning over remote sensing data mainly. So let's start. This training session, it's more like a gentle introduction of the data sets that we will use, the Python libraries. I will show how you can open the timeless and the temporal data sets that we are producing in the context of the project. And we will do everything inside the virtual box that we did share with all the participants. And in this virtual box, you have a complete environment with the data and without problems. But we have people to assist you the main reason it's because here we libraries work. So you have a hardware, your notebook, you have a operation system, could be Linux, Windows, it doesn't matter. And you can install like Python, and you have like some C++ libraries, so some libraries that are compiled specific for your operation system. And on top of that, you have several and when you are trying to develop like some application, like these cool spatial temporal machine learning applications, you use all these libraries, all this stack. And here, for example, we will use like the GDAL version 3.1.4. So it's a we will have a session specific for cloud optimized geotiffs to Can I continue? Okay, let me try. Stop sharing. Yeah. Okay. So to deal with this stack of technology, you have some options. So you can use Conda, Docker, and as we are using VirtualBox. So, and if you use Conda, for example, you can install in your operation system, and Conda will deal with all this system of dependence. And like, for example, if we install like if we use like a version of Raster which depends of a specific version of GDAL, it will install to you and it will manage to you. So it's pretty nice solution, and you can use in different systems, not just in Windows and Mac OS. You have also Docker. Docker, it's a bit different because you have like a complete environment, like really isolated with a specific operation system running like inside of a container. And in this container, you can set up with, for example, you can have like it running like in a Windows or in a Linux, and you can use a different operation system like Ubuntu or Fedora, for example, to put all your libraries and create it. So, and here we have like some links to set up like a container with all the libraries that we are using. And a VirtualBox, it's a different solution. So you actually you have like a virtual hardware where we install an operation system. So, and using this operation system, you can like use the own libraries. And if you think like in the problem that we are solving here, that it's mainly organize all these dependencies and provide like a stack of technology ready to use, these three solutions are really similar. But here we use VirtualBox mainly because we are embedding and we are putting all the softwares and all the dependencies so inside of the VirtualBox. So here we are providing like a specific version of QuantGIS with several plugins. We are providing a GRASS version of the new GRASS version 8, the whole environment for R, for Python. So specific for this training session, it's a nice solution. And something that it's interesting, so you can see that it's a virtual hardware. It's a kind of a virtual notebook or a virtual like workstation. You can play with the parameters of memory and things like that. So it's a machine inside of the machine. So if you think like that, it's good for the context of this training session. The downside, it's a big file, but you are receiving like much more because we are set up in everything and including the data. The data it's also here, but it's important to explain that this VirtualBox. It's better for the context of this training session. So because we are sharing all these libraries like softwares with interface and everything, but it's all in almost all cases it's slower than the real machine. And if you plan to do like a production work, it's better like migrate for solutions like Conda or Docker. So considering your environment. And for the context of this training session, later, for example, to use the libraries and to use the codes that we are providing here, you can, if you click here, for example, in this Conda env, you can see these are the libraries that we are using. So this is like a file to be processed by Conda and install all the libraries in your Conda environment. And here you can find like different Docker containers with R and using specifically, we are using this Docker container. So with Jupyter, if you install it in your system, and you can have it like you have instructions here, so you should be able to use and execute all the codes that we are Oh, sorry. Okay, so now I'm unmuted. Sorry about that again. So I will repeat what I explained, of course. So I was explaining about the Eomap library. So in this library, we created specific for the context of the project, and we developed several wrapper functions that use, for example, Raster, scikit-learn, and other NumPy functions to develop the products in the context of the project. So you can use this function to, for example, apply to apply in your own projects. But instead to use, for example, Raster, you can use like the function that we developed to read several rasters at once and read it in parallel. So I will explain how to do it. You can use the land mapper model class that we develop to, for example, try to map land cover using land cover and produce land cover classifications for using your samples and your specific raster data. So this it's more like a function to use all these libraries and to provide like easy access and functionalities on top of it, not to reinvent the wheel. And we will heavily use it, so probably you will be more aware of that, and you will understand like with concrete examples what how to use these libraries. And you have like official documentation here with some tutorials and some the API reference. So we develop like methods to do gap filling. So considering any type of data, climate data, remote sensing data. And we have some parallel helpers to implement parallelization. So it relies on job lead. So it's a kind of wrapper functions and class that you can use for the context of your projects mainly. And the other libraries probably you already know, like some like scikit-learn and TensorFlow, and we will use it and we will integrate to the Eomap library. And I specific about these three here, so Numba, Bottleneck, and NumExpri. You can these libraries are specific to optimize like NumPy operations. So during the high performance computing Python training session, I will explain how you can replace, for example, the NumPy operations like a regular mean using these libraries and really reduce the computation time. So it's we are using these libraries inside of Umap, but you can use for your own context, and we will use like a real world example, like an NDVI calculation, and calculating like median in these three libraries, and you can really show the difference and see the advantage to use it. And some of these libraries, like for example this Bottleneck, it's fully compatible with NumPy, so it's just a matter of replace your importation and you can start working with the methods. So it's pretty handy, and we have a complete training session for it. So now, considering what I'm talking now, so it's important to explain the context of the OpenDataScience Europe. So the OpenDataScience Europe, it's a data portal, a viewer that aims to serve decision-ready layers. So, and we have some examples here, like land cover, air quality, pollution, potential natural vegetation, and similar. And when we think in like decision-ready layers, it's there is like a complete workflow to prepare this data and to put it available and make like usable for multiple users. So in the context of the project, we are using just open source software. So, and we are developed like this new library also and put as open source. We are using like public available data like Landsat data, Sentinel, and data collected by modes, nightlight images, and collected by Swarm NPP satellite. And using these open source softwares and this public available data, we are creating like harmonization flow. So we are getting all this data and like cleaning it, preparing it, and create like layers that are really ready to use. So if you think like in a Landsat image, if you download like a regular Landsat image now or a Sentinel data, you have like clouds and you can have like one image specific for one date. For example, we can download an image of the last month, but to prepare this image to do machine learning or to do some type of analysis or a time series analysis, you need to do a lot of work. You need to harmonize the data, you need to remove the clouds, you need to prepare it. If you have gaps, you can't do like, for example, a prediction where you have gap, you need to put some value there. So you need to implement a gap filling approach. And all these types of processing we are doing inside of the project. So we are putting this data available. And for example, if you download like in this example, the Landsat or a Sentinel image, it's just for an area. But imagine that you are trying to process, for example, a whole country. So you need to download several images, you need to prepare that. And all these steps we are implementing inside of the project, and we are delivering like a complete data set for the entire continental Europe. So, and you can just access it and select, for example, your study area, and you can download the data and start working. And of course, there are some assumptions and some limitations of what we are doing because we are defining all these workflows, but we will explain how we are implementing it and providing all the means and the APIs, the URLs to access the data and to start work on it. So, and in the afternoon, we will see how to implement like these spatial temporal machine learning algorithms on top of it. So, and provide like, and produce like one of the land cover classification that it's one of the decision red layers that we already have available in the website. So I will show it to you. And so how we are like putting this data available. So we have, first, mainly we have the web viewer, but we also have a geo network. It's a metadata catalog. All the codes we are putting on in the GitLab, so it's part of this Eomap library, but we also have another repository where we are organizing all the production workflow. And the data, it's also available as cloud optimized GeoTIFF, and you can access through this URL. So we are preparing like a spatial temporal asset catalog. So it's a nice way to put this raster data available. But for now, for example, we can open the web portal and you can see all the layers here. So, and we are updating it like every month. We are putting new layers. We have more products that we will insert here. So this week we are preparing the classification for the 3 species with different, where we classify different 3 species all over the continental Europe, and like the actual 3 species and the potential where we can grow these 3 species. So, and here you can see all the layers available, and I will just show one example here. So this is the land cover classification. And you can see this is a temporal data set. You can play with the years here. And here we have like 2000 to 2019, but we are updating this data to produce a new version, reprocessing everything and generating, including the year of 2020. You can see the class here. So all the classes that we are classifying, and here, for example, this is the coniferal forest. And if you zoom in, for example, you can see the classification and you can play with the transparency. But also you can see the Landsat data that we used to process it. So for example, this is actually the Landsat data. It's one of the layers that we are putting available. And it's a ready to use layer. So we removed all the clouds, the most part of artifacts, and we are provide like a seamless raster layer. Here you are seeing the three bands, the red, green, and blue, but we are also processing like the near data and SWOR1, SWOR2, and the thermal band. So, and for the specific for the land cover classification, here you are seeing the hard class. So for example, if you zoom in here, you can see that this area was classified like coniferal forest because it's this like dark green here. But you also have like the probability layers here. And with the probability layers, you can see that you also has this for the whole years. And if you zoom in, you can see that some of the pixels are actually like with higher probability than others. So if you play with the transparency, you can see that here you have like less probability than here for the coniferal forest, for this specific, for this land cover. And in this workshop, in the training session, the context of the training session in the afternoon, we will produce it. So we will use like the land mapper, we use several machine learning algorithms to produce like a model able to classify the hard class, but also the probabilities and the uncertainty. So this, actually it's the same code that we use it to produce this product. So we are putting available this code and the data and the input data also to process it. And other layer that it's interesting is this one. So this is 1 kilometer land surface, but this is, so you can see that it's a more coarse resolution. So it's each pixel here, it's like 1 kilometer by 1 kilometer, but this is daily data. So actually for each year, for each day between 2000 and 2020, you can select like any part of continental Europe and you can see what is the land surface temperature, but also, for example, the precipitation. So this is other example of the data that we are preparing. So it's complete for the whole Europe organized. And for example, if you download it, you can get like the whole image, but we are providing the code to access just part of this data. So during the training session, for example, for the cloud optimized GeoTIFF, you can just clip on the fly this data and just download your study area or some region of your interest. So, and this is the data viewer. It's just to explore the data and to understand what you have available, but to access it properly, you really need to, it's better, we advise you to use the code and retrieve the information using, there are two options. You can use Python as we are using here, and or R. And the code for the Eomap, so it's the library that we used. You can access here in this GitLab. So, and all the training sessions we are putting here, the material, but the library is here, and here in the spatial layer you have like, we are putting like the workflow to produce it, but also the file name convention, how we are organizing this file. So we will explain it later during this specific session. And so I already presented some of the available data sets, but it's these are the main data sets that we have available now. So it's an annual land cover classification with the dominant class, probabilities and uncertainty, cloud-free Landsat R&D, so analysis ready data, and digital terrain models. So DTM, you have the slope, the elevation, and the hill shade, daily precipitation, and air and land temperature, as I presented. And we also harmonized some of the OpenStreetMap layers. So this layer here, for example, we took all the building areas and we just, we integrated with other building areas product from the produced by Copernicus initiative. And here we have like a better representation where we have like building areas in the continental Europe. So, and we are preparing actual and potential natural vegetation, a new version of land cover map, burned areas, and more. So till now, we built this infrastructure, and we are working with the workflow and with the code, and we are organizing all this data. So in the next one more year of project, we will prepare more data and put available in the same way. And here it's an example of the cloud-free Landsat data. So I presented it in the platform. So, but only to explain this, we are downloading like the Landsat images, harmonized and provided by University of Maryland. You can find the reference here. So they implement a complete workflow here just to harmonize the satellite data between the three available Landsats. So Landsat 5, 7, and 8. And it's a pretty challenging work, do it. So, and they invested a lot of time. So it's something that you need to be aware. It's not to download the data that we have available for Sentinel or from USGIS, Landsat data, and start working. So you need to prepare this data. And if you plan to mix, for example, different satellites, it's way challenging. So they organized this product, and on top of this product, we downloaded all the data since 2000, and we organized it in seasons. So for each year, you have like the winter, the spring, summer, and fall. And for each of these seasons, you have like different percentiles. So it's a kind of way to capture the seasonality inside of each season. So I will explain it and I will show some examples. And on top of this, we gap filled all the observations, because even, for example, in the winter, if you remove all the clouds, probably you will cover like 60% of Europe. So we processed it and we gap filled using other seasons and other neighborhoods observations. And here it's an example that we prepared. This is for the spring. So you can see for the whole Europe. And now we are producing a new version of this product. So the data set that it's inside of the VirtualBox, it's already with this new version. So we have the whole the workflow. It's implemented, so it's just a matter to improve the algorithms and reprocess everything. So we will keep maintaining it. And here it's an example of the gap filling. So this is the data with gaps. So we removed all the clouds, and for some seasons and for some parts of Europe, we don't have any observation available because everything is cloud. And so you need to put some value there to really enable run it on a spatial context. You need to have a pixel there, but of course there is no magic. So we are explaining in the inside of the library, there is a tutorial about it, but there are some ways to do it and to implement this gap filling approach. And here, the data that you will use during this training session and the next one, it's already gap filled, so it's the final data. This is just an explanation of what we did. And so inside of the VirtualBox, you will find this folder here with the data, and mainly you have available two tiles. One tile is for Farming, this tile here. Another is for Greece. And inside of these tiles, you can see like different folders. So this is the theme of the layers. And inside of these folders, you have like these files here. So here it's the blue band of the Landsat satellite, and you will use it to access the data and read it. And I will show how to do it in Python. And so before to really go to the code, I would like just to explain the training sessions and how we organize it. So this training session, it's the introduction to OpenDataScience datasets in Python. So we will have like a view of the datasets and you will access it. And I explained it about the environment. And after that, you will have like the introduction of spatial and spatial temporal datasets. So mainly we will show how to do like the space and space-time overlay and how we implemented it inside of the Eomap. In the afternoon, we will have the spatial temporal machine learning. So it will be a long session because we have two parts. And in this session, mainly we will use a random forest to produce like different versions of land cover classification. So we will start with a pretty regular random forest. We will implement a hyperparameter optimization, and we will use this random forest to produce probabilities, and we can see like the evolution of the results. And the last exercise will be how to implement, like use multiple learners. So we will use like artificial neural network, a random forest, and an XGBoost. It's a gradient boost in trees. We will use these algorithms to produce like an ensemble machine learn, which combine different approach, different models, and produce also like probabilities, dominant class, and uncertainty. So currently, this is our workflow. It's the way that we implemented this land cover available in the website, and there are some advantages, and I will explain it. And tomorrow we will present about the harmonized Lucas dataset. So how we prepared this survey dataset available for Europe, how we prepared it in the context of the project. And later we have like a session to optimize your workflow and your processing Python, like high performance computing. So I will explain how we are doing it inside the project and which libraries we are using and how you can reduce the computation time. So there are some options in Python, and mainly how we are processing, for example, the whole Europe. Of course, we can do, it's not possible to do it here in your notebook because we are using several servers to do it. but the general concept of how we are splitting the processing and how we are organizing the results, it will be presented. And the last session, it's about the cloud optimized GeoTIFF, and it's mainly how you can access the data through API and use Raster.io to visualize like a thumbnail of the data just in matters of seconds, like in the whole Europe. So, and clip the data and consult, for example, like a time series for the NDVI 20 years. So we will provide the codes and some concrete and real examples of how to do it. So yeah, now it's time to work with the code, and mainly in this session I will present how to access this data. So we will work with the data that it's inside of VirtualBox. So it's important to have the VirtualBox, and it will minimize the access to the network for now. And we can start working actually with the Jupyterlab now. So before, I'm sorry, I forgot to introduce like the other instructor. So we have Chris from OpenGeoHub. He's here to help you. And we have Luca, who will lead the other training session about the introduction to spatial and spatial temporal data. And we have Martin Landa, that he will lead the working with harmonized Lucas dataset. So if you have problems, of course, here they can help you, and we are online in the Mattermost to check the questions and to provide support for the online participants. So before I start, we have some problems with the internet connection. Now it's normalized. Let me see here. I don't know. So no, I think it's working now. Like it's
working. So if you experience connection issue, you can connect to that.
Okay. Okay. Thank you. So for the next training session, we will migrate, and I would like to thank you, Patrick, to help us with this technical issue here with the internet. And so let's open the Jupyter notebook. So you can see here I'm already inside of the VirtualBox. I will just like close everything here to explain to you. So yeah, in this VirtualBox, as I said, you have all the softwares that we will use. So, and these are the credentials. So every time that you need to provide a password or a username, you can use it. ODSE hashtag 2021. So in this session, of course, we will use the Jupyterlab. It's a pretty nice development, integrated development environment built on top of Jupyter Notebook. And if you open it, I will close it here. So you should be able to see like the environment. And if you click here, let's click here first and close all the tabs. So before we really start working with the code, it's important to explain that here, if you open here in files, this is a Ubuntu operational system. You can see we created this ODSE work dir, and here you have the data, the code, And here we have some styles that for the spatial layers in QGIS. So for the code, you should use this one. This was just a draft version that I forgot to remove in the VirtualBox. So this one, it's actually the official Git repository for the codes that we are preparing here. So, and when I prepared like the VirtualBox, this is already linked with the GitLab, but you need the first thing really, it's you need to update the code here. So to update the code, as we already, this is already a Git repository, you just need to open like a new terminal here and just type git pull. I don't know if I need to increase my font size. It's okay, or it's better if I increase. So with this, it's just a regular git pull. My repository, it's already updated. So, and again, you need to do it like inside of the ODSE workgear code and ODSE workshop. So, and this will bring all the new source code that we prepared and the Jupyter notebooks and everything. So this for sure should be the first step. Now, let's go back to the Jupyterlab. So, and inside of the Jupyterlab, so here we have all the libraries, GDAL, Raster, Scikit-learn, but you need also update the Eomap with the new version, and this setup doesn't provide like the TensorFlow we will use in the afternoon. Because it's a trick dependency, and if you use, for example, TensorFlow in a GPU, in a server with a GPU in your workstation, you need to set up it properly, and in this case, you actually need to install a pretty regular TensorFlow, but it's why we didn't set up here. So to update the Umap, you need to use this command here. So it will get the new version of the Umap directly from the repository. And I shared these slides in the by development channel in the Mattermost, but you also can find this line in the Eomap installation. So you just copy it, but it's better copy from the slides because you can see that I'm using like a sudo to install like inside of the Jupyterlab. So here you need to update your version. So you can just copy here and download the first, download the new version of the Umap, and also install the TensorFlow. Yeah, if you to copy here, I'm using Ctrl-Shift-V. So yeah, this that's all. So first you need to update the training session repository. So I will show again. Here you just open code, you go to, you open here. Oh, really? Let me see here. Okay. I think now you should be able to access, sorry. Okay. So to update the repository, it's just enter in the folder, git pull. So inside of the ODS Workshop 2021, and in the slides, you have like the instructions to install the Eomap and the TensorFlow. Any questions, problems? Okay. So inside of the Jupyter notebook, you have the same work here, and code. You need to open the same folder that we prepared with the GitLab repository and Python training sessions, and you have this the first one, the introduction to ODSE datasets. So we'll work with that. So should I increase the font or it's okay? Yeah. Yes, the password is this one. Yeah, if because the first time maybe it asks for the password, this one. Okay. All right, so is it work?
It's like token to access the Jupyter instance.
Not really. It's
Yeah, we tried it.
Yeah.
ODSE.
2021. Now invalid. ODSE. Hashtag 2021.
yeah. Let's see here. Where is the hashtag?
Is it the
Yeah,
maybe
probably.
the keyboard in the
Yeah. Probably it's because the hashtag it's
use this hashtag?
yeah. Yeah. This hashtag it's tricky. Yeah. In the Zoom.
Yes.
here. Chat. Okay, how to update the Eomap? Yes, so you can find the line to update, the command to update the Umap here. So it's mainly like a installation of a Python package directly from the repository. So you just need to copy this line and go to the terminal inside of the Jupyterlab. It's important to be inside of this Jupyterlab because it's a here we are using like an instance. And so to copy this line here, actually I'm using Ctrl-Shift-V. So yeah, that's the tricky part. And it will update. This line, it's already in the official, it's also in the official documentation, so you can use it, getting from there. But for the training session, it's important to install as sudo because we had some problems with the setup of the VirtualBox. So, okay, so let's continue. So in this Jupyter notebook, we will mainly explore the data that we have available inside of the VirtualBox. And as I did show in the presentation, we are working with two tiles. So there are like regular regions inside of the continental Europe, like each of these tiles has 30 by 30 kilometers, and we are using like this tiling system provided here. So we develop it specifically for the context of the project. But let's take a look first in this tiling system, and we can explore it here. So first, I will restart. I will clean all my cells here. Restart the session. Yes, this one. So first, we will import like some libraries. Basically, we are using Pandas, NumPy, and GeoPandas. GeoPandas, it's a library to access this the vector data, and it's built on top of Pandas. So the first thing here is this tiling system. It's just like a geo package file that we prepared for the project, and inside of it we have like these regular tiles, and we use it a lot inside of the project to split the process, and here we are using it to provide two specific tiles for you. But what it's interesting here in this part, it's mainly that you can see that the file it's actually not here. So we are using this URL. So this file it's hosted now in the our S3 servers, but you are accessing it like using a URL. And if you send it for the GeoPandas, you can see that you can access the data. So this is it's the beginning of how we can how we want to provide the data for the user. So everything is in the cloud, it's hosted in public URLs, and you can access it through the API. You can also open it in QGIS. I will not do it here, but it's possible. And so you can see it's a pretty regular table with some parameters, and you have like a geometry here. But as we have a geometry, we can use it to open in the IPy leaflet. So it's already set up here. This package and this library, sometimes it's tricky to install with Jupyter Notebook and in the Jupyterlab, but here it's already working. And what I will do mainly, it's just plot the tiling grid system here, and I will use like as base layer, I will use this OpenStreetMap. You have different base layers options in this IPy leaflet, and you can use, for example, Google satellite images from Esri. So here it's just like a pretty standard way to how to access and plot like a file here. You can see this is actually the tiling system. So we have all these regular grids cells here. And if you zoom in, so for example, you zoom in here and you can see that it's just like a vector that we are showing here. And as it, considering the number of tiles that we have, it's more than 7,000. Sometimes this library has problems to visualize. So it's why I just like removed it and to navigate, and later I just open it here. So mainly it's just a way to visualize it inside of Jupyterlab. But specifically for the training session, you can see that we prepared here in the data, we prepared these two tiles. So this is actually the ID of each of the tiles. And inside of it, you have like a lot of folders, not a lot of folders, a lot of files. And what we will do now, it's just select one of these tiles and prepare like these two variables. So you can see this is the where we have the data inside of the ODSE data gear, like ODSE work gear, and we are using this tile. So we will use this variable like this raster gear across the entire Jupyter notebook. And so now I'm just using this raster gear, and you can see I'm using like this raster gear. I set up as a path. So it's this is a new like not really new, but it's a nice way to access it in the new in the Python 3. We have this library like the pathlib, like this model actually from the official Python, but it's pretty handy to access and work with these gears. And so here we are just listing all the files. So you can see that it's a lot of files. So because we took multiple layers that we prepared and we just clip automatically, we did clip for these two regions. And I will just list some of them here so you can see. And if you use like this raster dir, and as it's a path, you just get the name here. So this is the name of the files. So, and let me just delete this because this is the result of the next session, and I will delete it also. It's not necessary to do it actually for you. And okay, so it's here I'm just reading the data to explain that we have this available in the, and right now so it's a lot of files. So a nice way to organize it is it's really like you can read these files, but you need to have a summary. So you need to understand what it's available. So what we have in this section here, Raster Summary, it's just a way to organize the files and create, like, aggregate all these temporal layers. So you can see here that you have available this DTM hue shade. So DTM, it's just like the layer that are available for 1 year. So we are calling it as a timeless layer. And you have like a temporal layer. So for example, you have a Landsat, image, red band, and percentile 50, and you have this same layer with the same like properties you have for different dates. So it's a temporal layer. And land cover, it's also a temporal layer. So you can see here that if you look for this DTM hue shade, you have 2 DTM hue shade here. So, and basically they were generated using different parameters, but it's like 2 separate layers. If you do the same thing for the Landsat, you can see that you have this land cover, red, Landsat, GLAD, R&D, and you have this start and the end date. And it's the same file name, like this part of the name, but we are changing the date. So inside, using just this file name, you can retrieve the information for the period that you want. So and you can work with that. So the most part of the data that it's available in this folder, it's actually temporal data. So it's why we have this number of files when you just try to list them. And to understand the file name convention, so you can use this code here. So in that GitLab issue, I will not open here because we are running out of time, but here in the top, you can see that we have like a file name convention here. And yes, and what I did here in this cell, it's just, I'm splitting the file considering our file name convention. So you can see here the variable code, the vertical dimension. So all the data produced in the context of the project are following this file name convention. And you can play with that. I don't know, you can put 100. So, and you can see these files mainly. Here it's because I extrapolate the list of the files that I retrieved just for the red. So you can see that it's just like changing the year here. So what I will do now is I will retrieve all the files and organize it in a table. So, and in this part, it's like an aggregation to combine all these temporal layers. So, and you can see that it's just, it's a code to split the file name using our convention and create this raster summary, but without the date part. And you can see that, for example, for the Landsat data, we have 84 files. And this, it's a kind of, it's like a summary table to help us and to understand what we will read. And you can open in the QuantGIS and you can check, but it's a nice way, for example, to check if you have like land cover data available in that folder, because the number of files that we have, it's too much. So it's just a way to organize it and provide like a easy access to all the data. So using this table, you can select like one of the layers and start really open it here in the session. So what I will do now, it's just use this Eomap library. If you click here, we develop like a raster model to read the data. And of course, you can do it also with raster.io, but the main advantage to read, to use the raster, the read raster, it reads the files in parallel, and you can work with multiple files. So it's really handy to use with the temporal data. So I will show it in the next minutes. So it's just here, I'm just importing the read raster, and I'm using like find files just to retrieve the files, and it's just send the files directly to the read raster. So here I will read the 2 DTM layers that we listed. And the result of it, you can see here, you have the data, and the second argument is the file names. I already have here the file location, so I'm not using. And basically, this is a NumPy array. So it's a data, I just read the data, loaded in memory. So now we have a NumPy array that will allow us to process all the, to process it and do some operations. So for example, and you can see that as we read 2 files, so here it's the first one, here it's the second one, you have 2 dimensions here. So the raster, the read raster, it's a like a helper function just to read different files in parallel and aggregate it as a NumPy array. So, and using these files, you can see it's possible like calculate some statistics. So here I'm just getting like the minimum, the median, and the max value for each of the files. So, and you can see here, it's the data, it's compatible with all NumPy function, because it's a NumPy array. But of course, we can plot it. So we can plot it as histogram. Or you can plot as like a raster data. But let's open the same file in the QGIS just to understand this data set. So you can open here. And in QGIS, you can open like a raster layer. And you go to the same folder. I get this one, DTM, and I will open the 2 shades. It's just information about the projection system. So you can see this is the data. It's the same one that we are seeing here, and it's a pretty regular like image, and it's one of the tiles that we are working in the project. Here in the QGIS, you have much more options to visualize it, and so this is one of the reasons of why we are using this virtual box. So you can see here the web. You can see that you have this plugin, quick map service. So, and you can use different base layers. So you can put like a satellite image here, and now it's better because we have a context. of this region. Here, this, and you can zoom out and you can see that it's in Greece. And with the hue shade, you actually can understand a bit better the image here in the Google Maps. So yeah, at this moment we just load the data in Python, and I explained about the file name convention, and now we are ready to read the temporal data set, like the Landsat data set. And one question, how we are about the time? Yeah, we have problems in the beginning of the session, but so I will open I will open the Landsat data, and the rest of the Jupyter notebook we will present in the other training sessions, because it's just like some operations with this NumPy array. But for this session, it's really important to understand the data, show where the files are, how to open it in QuantGIS, and how to open these files like the temporal data, because it's one of we will use a lot this type of data. So I will pass through this explanation of how the data was generated, but you have like some context here about the seasons, and I shortly explain it during my presentation. So what we will do now is just load like this complete time series of Landsat data. So all the available seasons and years that we have for these tiles. So here you can see in the Raster Summary, so it's just a table that we prepared with the data. So, and you can get one of these layers. I will get like the near band, so the infrared band, accurate by the Landsat satellite. And here you can list all the files. So it's this find files is just a method to find specific the file. And here I'm reading like all the, for this specific date, actually, I'm reading the 3 percentiles. So during the land cover, I can explain about it, but it's just like these percentiles, it's a way to capture the seasonality inside of each season. But, and you can see there, it's 3 files that we retrieve. And if you open it with the read raster, you have like a NumPy now with 3 dimensions. So during the other training sessions, we will use a lot this method, because it really like read all the data and stack and provide like a structure to work with that, to do some operations and to calculate machine learning and to apply some reducers as median and maximum. And you can do the same thing as we did for the DTM, and mainly you will see that the minimum, the median, and the maximum value, and the histogram, and you can plot it. So here we are using a different color, but you can access and see the data, but it's just like this plotter, it's more like to a quick view. To really understand this data, of course, it's better open in QuantGIS. So we will do the same thing here. So you can just go to QuantGIS, raster layer. So you have all the bands here. I will just go to near. And I will get like just one season specifically. And I will add like the percentile 50. And here. And this is the other tile. And this is warning. And I will apply like a color scheme to it. And with the Google, you can really see like the satellite image. Here I open with the gaps, so it's why I'm not getting it. Okay, this is the right one. Yeah. And yes, this is just an example of how we can open the data in the QuantGIS. And yeah, and I will put here just to compare with the. And we will use all this data in the next sessions. So, and this is like the same data that we open in Python. And yeah, and we have some other parts here that reads more data and do some operation, but we will work with that in the next sessions. So here we stop the presentation, and I'm sorry about the technical issues, and I think now we have a permanent solution, and thank you for the attention.
Okay, sorry about that. So hello everyone, my name is Luca. I'm doing the training session about introduction to spatial and spatial temporal data in Python. So the outline of this workshop: first, I would like to start with some spatial referencing basics, because I found that a lot of experts that are proficient in GIS actually sometimes forget the basics of of coordinate reference systems and what they mean for the data. And even myself, with actually a background in geodesy, I need to remind myself this sometimes. So yeah. Next, we will continue with raster IO and manipulation, and after that with vector IO and manipulation in limited capacity, because the rest of the workshops are mostly focused around points. So we will limit ourselves to that. We will then compute a basic time series and go through some, if there's time, go through some Eomap convenience and performance utilities. So to continue, so what is actually spatial data? It's data in a spatial context. So when we say spatial context, we usually mean where the data is placed somewhere on the surface of the Earth, but spatial context is more than that, because we build multiple layers of abstraction around the Earth's surface. So we have, like, first there's the surface of the Earth, then you have a terrestrial reference system. Then you have an ellipsoid, and then after all that you have like a surface that you project ellipsoidal coordinates on. So yeah, we need all of that to put data in a spatial context. So rasters are positioned basically with multiple parameters. You have the coordinates of the upper left angle of the raster. You have the size of the pixels, which is actually defined by 4 parameters, 2 of which are usually 0. If you see the BND, the BND, sorry, and if maybe some of you recognize this image below the left side, it's from the Wikipedia page on Esri world files, which is an Esri world file is basically what positioning a raster in the spatial context is. It's an affine transformation. And vectors are positioned in bits of a simpler way, which contains more data, but the data itself is written into the vectors. It's just coordinates of each vertex. So yeah, the x and y coordinates in the context of the geospatial data are referenced to the projection surface. This is also true even for 3D data, because elevation data is a thing of its own, basically, usually. So the quality of a coordinate reference system really depends on what you are using it for. So basically, for mapping, topographical mapping or web mapping, if you like navigation maps and that, you would use a conformal projection, because it preserves angles, so things retain the shape of how you know them. But for quantifying surface properties, for example, you would use equal area projections, like we use for OpenDataScience, because that's what we're doing here. And why does any of this matter? Because we use data from all kinds of sources, and we forget that it might not be compatible with one another. So you can have like, well, if you have like continuous data, then if you reproject it in another CRS, then everything is probably fine because you interpolate it. But if you have nominal data, like for example land cover, you cannot interpolate it. So you do like a nearest interpolation, and you have pixels that are that are largely different shape, and if you compare them with another, for example, nominal data set, your results would not really hold water. And also with vector data, there's things like old coordinate reference systems, like for example in Croatia. We have, before the current system, we had inherited a system that was from the Austro-Hungarian Empire, which had a local ellipsoid. And people are still having trouble to this day converting data from before to our new system, because you basically get vectors that are 400 meters away from where they should be and stuff like that. So yeah, all of this being said, you won't have to deal with this during the course of these training sessions, because all of the data is in the same system and all of the pixels are aligned in exactly the same way. So yeah, let's continue with the practical part. Okay, so before we start, if you joined the previous session with Leandro, you don't have to do this, but if you are just joining us now, please update your notebooks like this. So you go to this directory and just type git pull. So okay, we can begin. So yes, again, this session is very introductory. So if any of you are joining this just because you're joining the entire Python track, then sorry if you are not going to see anything useful, but yeah, so let's begin. So yeah, we'll cover the basics of accessing basically and manipulating data in Python using the standard tools, which are Raster, NumPy, GeoPandas, and also Eomap, which has some performance and convenience-oriented functions like Leandro already mentioned. So yeah, okay. Let's clear all the content. So let's begin. We will gather some files. I'm not sure if, yeah, Leandro already mentioned all of this. So this is, we will use this style ID. This is the data there. We can just go ahead and run this. We'll get a bunch of file paths. And then we can open, we'll open the second file in the list. And then we get a dataset reader. Dataset reader is a Raster IO object that enables us, of course, to read files and contains file metadata. So if you run the next cell, you see there's the driver, geotiff. There's the number of bands from the file, the shape of the raster, the coordinate reference system, and the transform. No data value as well. You can actually see all of this in the raster profile. Well, maybe don't print it. See it better this way. Oh no, it's the same. Never mind. So now, if you read the data, you can put the number, the band index here. Here there's only one band, so it doesn't matter. If you do not put the band index there, it reads all the bands, and just if there's only one band, it just adds one more dimension to the array. So we're going to go ahead and do this. So when we read the data, we get a NumPy array. And we can do with it whatever we could with other NumPy arrays. So we can do this. We can compute with the methods of the array. We can also do some stuff which we'll get to later. We will do that, compute some statistics, and then plot with the plotter from Eomap. So yeah, this is the raster. I think maybe the picture is a bit big. If anyone is wondering why the fixed size is only one number, if you're familiar with Matplotlib, it's because the other axis is computed automatically to preserve aspect ratio of the rasters. So yeah, so here we have a what was it? It was a blue band, I think. Yeah, blue band. Well, it's not blue. Let's make it blue. Okay, so here's the blue band. So now we get to do some stuff with NumPy, because NumPy does enables you to do computation basically parallel under the hood. You don't have to think about parallelization, and does it on its own with the BLAST libraries. And one of those things we can index. We can compare arrays to a number in a vectorized manner, and then index them with what we get from there. So yeah, here we'll compute the 20th and 80th percentile. If you're concerned with the usability of this, don't be. This is not about doing something particularly useful. It's just to go through some things one can do with rasters, with the Raster.io and NumPy. So yeah, we'll compute the percentiles. We'll compare the data with the high and the low percentile. Then we will combine the index with a bitwise OR. So bitwise means you compare basically the indices element by element. So you have two arrays of Boolean data, and you compare them element by element, so you get a combined index. And then we can calculate the percent of data outside the bounds by this code. So yeah. So this is what we get. This is the low percentile. Oh, sorry, this should say 20, not 5. And this should be 80. Yeah, so the low and high percentiles. And the index is like I said, an array of Boolean values. So we can then use that array we will first create a copy of the data, so we don't soil our original array, and we will index it with this. And say that all of these pixels that are true here should be no data, and then plot the results. Now, again, reduce the size a little bit. Yeah, okay, so you see now that a lot of the raster is now no data. Or we can do something that's usually more useful and actually clip the values to the low and high percentiles like this. So we index first with a low index and say that the values should be low, and then with a high index, and they should be high, and we can then plot the results again. Yeah, again, let's make this blue. Okay, actually, let's not make it blue because you can't see the difference here. So I'm going to go back to the previous image and actually just let's plot them next to each other. Data and new data. Let's add another title here. We don't need the F there. Yeah, okay, you can see the title very well. Let's do this. Yeah, okay, so you can see the reduce of variability in the data because the right one is clipped. So if there's something we can notice here as well is that this corner here and this cutout here that were previously no data are now actually clipped because no data of this raster is 0, if I remember correctly, which is lower than the low percentile, and we did not do anything to account for that. So what we can do is this. Raster.io enables us to, we could also compare just the data to the no data value and then produce an index that way, but the more efficient way is to use the read masks from Raster.io. So we read masks from the same band. We do this as type bool to make it a Boolean array because you get uint 8, I think. If you don't do that, then we can do this again. So we get only the pixels where there's data. So we can compute only on them. So we get data only. We do the indices. We compare the data pixels to high and to low. We again clip them. We make another new data array. We fill all of it with no data, and then we can fill only the pixels that's under the data mask with what is contained in the data only array. And again, let's plot the old data here as well again. Oh, sorry. No, 8. So if you can see there, the no data is now accounted for. So we have made a new raster, and let's now go ahead and write it into a file. So first we will create a directory with this part here. Then define the path of the output file, and we can use Raster.io dataset writer as a context manager, as one would with a regular open from the Python standard library. But aside from the output path and the mode, which is the right mode here, we need the raster profile. So if you remember the dictionary that contained all the raster metadata, well, we can just pass that here as keyword arguments because we haven't changed basically anything other than the data itself. So the data type is the same, the CRS is the same, the raster size is the same, everything is the same except the data. So our new raster basically has the identical profile to the new one. So let's go ahead and write it. You can see we have here a dataset writer object, and it wrote to the file. So just to check, we can use plot rasters with a file path to see what was written. Again, reduce the size of the plot. So there we have it. So now to some vector data. For that, we will use GeoPandas library. That basically it's pandas, but for spatial data, it has GeoPandas data frame. It basically differs from the pandas data frame by having a non-optional geometry column on which you can compute geometry operations. So we will go ahead and read the land cover samples that Leandro mentioned in the session before, and print some data points, and then look at the points themselves. So if you ignore the runtime warning there. So yeah, the CRS is the same as the raster data. Here we have the number of points, and these are our points. So we will not be using any of the data in this data frame. Actually, in this session, we will only use the geometry. So yeah, it was mentioned that IPy leaflet is useful for visualizing data in spatial data in Jupyter. But if you need a quick and dirty way to compare the extents of data sets, this is one. So basically, you can import Shapely, so box and multipolygon from Shapely geometry. Shapely is a library that GeoPandas uses under the hood. But used to, now it uses either that or PyGeos, but yeah, we won't get into that here. So you create a box from raster extent, and that creates a polygon. You then do the same with the points. So you do this. Cascaded Union is if you have a relatively small data set, you can make the entire data frame into a single Shapely geometry, so that it visualizes easily in Jupyter, and also you can compute bounds on the whole thing, basically. So yeah, we can do this. We have two polygons, and you can see our raster is here in this little corner. And this is the point. Well, actually, points are just here and here, but yeah, we will just what we will do next is take only the points that intersect with our raster. So we can do this. We create an index by using the points intersects method. So you just pass it another geometry, and you get a Boolean array that contains true or false, depending on where the geometries intersect with what you have here. So yeah, let's print the number of points we get now, and let's also visualize the point subset. So yeah, these are our points now. And we can also write vector data sets. So right now we have to do this because there's a bug with the current version of Fiona. So if you don't do this with, at least I think with our point data set, it produces an error. So basically we have to do this, but yeah. So what is important here, other than the error wrapper, is you just do this point subset to file, and then you define an out path and say which driver. You only have to define the driver if you're not writing an Esri shapefile. because that is the default. So yeah, we now wrote that to a file. So on to computing raster time series. So yeah, like Leandro already mentioned, there's a helper in Eomap that enables you to read a bunch of rasters multi-threadedly into a single array, so you don't have to go through all the files manually and then stack the arrays and all of that. So we will go ahead and take all of the Spring dataset, all of the Spring rasters for red and for near infrared for this style that we were already working on. So yeah, here are the shapes. As you can see, these are stacked like a multi-band image instead of being this axis being on the front where you have like a list of raster datasets. So yeah, we can basically just do this. Raster datasets are arrays. You can do this. You can compute with them directly, and this is how you compute an NDVI time series from the time series of red and near infrared. And we can also index 1 point and 1 pixel well, and we'll plot a series for it. So yeah, that's that. So we can also plot the entire series with plot rasters. And I'm not sure if we have to do this anymore. I think Leandro maybe patched this last night, but I'm going to go ahead and do it anyway. Anyway, just move the axis that contains the bands to the front. So that the shape of the array looks basically like this. And yeah, we're going to plot the rasters now. I think I can increase this a little bit. So yeah, there we have it. We didn't plot the entire series because it'll be 20 rasters. Maybe take a while. We can try it, but yeah. So we can now compute with this series. We can, for example, compute the difference of each year to the previous one, which is basically just differencing the series from itself with a shifted index. So we take here the last 19 images, and then we subtract the first 19 from them. And then we can also plot the results. So yeah, now you can see differences from each year to the previous. Or you could say you want to compute differences from the first year. Just do this. But yeah, well, let's get back to the previous year differences here. And we can use the Umap helper function to save the rasters in parallel, of course. So yeah, we define the file names here. And we write the files. And also, yeah, we need to put here a path for a reference raster, which then say rasters takes the profile from, if you remember the raster profile you need when writing rasters. So instead of putting that there, you just give it a reference raster to take the profile from. So yeah, basically we unstack the data again to be a multi-band image, because that's what say rasters takes. And we also should define the no data here, because the default is 0, and the difference of NDVI from one year to the next can definitely be 0. So we should change that. We also change the data type because the GeoTIFF driver does not accept float 16, which is what our data is, because we computed from the start with 8-bit integer values. So it tries to keep the memory usage low by using the lowest possible float. So yeah, let's save the files. Then yeah, here save rasters just outputs the file names that we saved data to. So what we can do now with these files, we can use the overlay helpers from Eomap Mapper to overlay all of the rasters at once with the geometries. So this optimizes things a bit, and so let's run it. So is it done? It's done, I think. Yeah, it's done. So you basically give this function, well, this class a bunch of geometries as a GeoPandas data frame, and just a list of the files that you want intersected, and it does the overlay for you. So now we have time series for each of the points. So you can see the column names are just named after the years. So let's plot the series from a single point. For a single point, we are going to sort the columns here because they are not currently sourced by year. And we are going to take a series from a single point and just plot it. So yeah, as you can see, series at this particular point. So now onto some convenience functions from Eomap. So yeah, Raster.io allows for windowed reading of rasters. So if you do this, if you define a window, you can read a raster with that window. So only the data from the window will be read. So if you do this, so you need a column and row offset and width and height in pixels. So yeah, now we have a 5 by 5 pixel data set. But what matters here for large files is that Raster.io has to read the entire block of the raster before it reads that particular window. So if a window intersects with multiple blocks, then it has to read all of the blocks before reading that window and just outputting you the data. So if we look here at the number of windows that our test raster has, we can just do block windows and just expand it into a list because it's generator. So yeah, 125 blocks. So yeah, but what we can do with Eomap blocks, basically we can read a large raster by just reading it block by block, windowed, and we can not worry about that, let it run in the background and just define something that we would like to do with the data from each block when it's read. So we can do this. We import mapping from Shapely and take the URLs for Landsat red and near infrared for 2018. This is summer. And so we will define the file URLs and define the geometry. The geometry has to be given here as in the GeoJSON schema. So we do that with Shapely geometry mapping from our Shapely geometry. So yeah. So this is the raster that the size of the raster that we are going to read now, as opposed to 1,000 by 1,000 pixels that we were reading before. And this is our geometry. So we import from Eomap parallel blocks, we import the block reader, the block writer, and that's basically it. All we have to do now is define NDVI as a function that will be computed for each block. So we initialize the reader with the reference file. And here, all of the files that are read have to have the same transform, and the blocks have to be identical. So this is for reading those kinds of data sets. So we give it the read URL as the reference file. Then we initialize the block writer with the reader. You can also omit this, and you can just initialize the writer, and then that will initialize the reader with the first file. But just to illustrate, because the reader is then reusable, it initializes by computing geometries for each block. So it can take a while. So if you are going to reuse the reader class, the reader object rather, you should initialize it on its own. So if we run that and wait a bit. So if we check, oh, it's not done yet, okay. Sorry, I should have run this, yeah. Okay, so if it's done. So we defined our NDVI function here. We defined an out file. And then we called writer write with the source paths and the destination path. And also the geometry, the function that we want to compute, and should give of course the no data value, because again I think the default is 0. The D type, and now let's see if our files have written. Our file, sorry. Yeah, so this is the same block, but computed from very large files that are hosted on S3 buckets. So you do not have to download the entire file to work with it, basically. And yeah, so the final part here is I would like to talk about some convenience abstractions around the catalog of the data produced and also used by Open Data Science. So as you know, as Leandro has mentioned, we have the catalog in the Geo network, but from a Python standpoint, you would have to use CSW from OWS lib to access that directly. So here we have a catalog object that we import from Eomap datasets. And then we can search with it. So here the catalog also has a fallback copy of the basically of the entire catalog as a CSV that's distributed with the code. So if basically if maybe you're having connection troubles and your network can also be a bit slow, you can just use this, and that's what we're going to do because it's faster and the fallback CSV is updated, so there shouldn't be any difference between the two right now. So yeah, here we have a resource collection. So yeah, the output is grouped by metadata. So all of the resources that have the same abstract theme and title. So this is NDVI Lancet Quarterly. They're grouped basically, but you can use the results object as you would a list. So we can just do something like this, basically results. So to get the first three of them. So yeah, these are, and if you look at only one of these, so these results objects are basically strings, so you can use them as URLs for files to use with Raster.io and the Umap helpers, but they do contain additional metadata. So if you want only the metadata objects, you can do this. So here is the metadata. But yeah, and also there is the metadata of the collection object. If you want to access the metadata groups of results. So if we have 0, that gives us the NDVI, the quarterly Lancet NDVI. If we index the 1, we get this, and oh no, there's no 3. Okay. So yeah. Okay, this output is a bit long, so just scroll down here. We could also you could exclude the results with the search, so we don't have to sift through them manually later on. We can just exclude with the exclude keyword. So if we exclude the trend, we just basically get this. So yeah, let's check results meta. So yeah, there's basically only the first one. Again with the long output. Yeah, okay. And we can also search by year. So here we get the quarterly Lancet for 2019. If we want to say search by multiple years, so we can here input range, for example, from 2015 to 20. This is non-inclusive, so we should be okay. Then you have, then year is added to the metadata, and you get groups of resources by year. So if we do this, so that's now just the first group. So only the rasters from 2015. So yeah, we can use now these resource collections to read directly from the files. So we'll use the read rasters. And read rasters also takes a window object. So we will define a window like this. So yeah, the raster window submodule has this from bounds function, which takes basically the bounds. So we will give it only the bounds that we were using so far. So the extent of the test raster that's included in the VM. We also have to define a transform. We can also just read from one of the files. So we get the first file. We just do this. If you remember, it's what Raster dataset reader contains of all of the metadata like this. So yeah, you define a window here. You just basically use read rasters as we did previously, but you just say you use the spatial bin keyboard argument to define a window. And this part here is basically the catalog result resource. So this should behave like regular strings, but there's currently a bug with that. So we just convert all of them to strings. So we run this. And then we can plot the results. Okay, this is a bit too small. Again. Okay, let's instead just what no, we can do that here actually. Last 5 of them. Oh, sorry. Yeah, so these are the windows read from directly from the rasters that are hosted in S3 buckets. So okay, So this is the end of the plan section. So we have some time left. If you have any questions, if you would like to suggest that we try anything, or are there any questions on Zoom? No? Okay. Leandro, would you like to use the time left to go over the things from your last session that you had to skip over?
I can just explain it.
Okay.
So I think that's a good idea.
Okay, yeah.
And yeah, so you already covered some parts, but
Okay.
I can open and explain a bit. Yep.
Okay, great.
Thank you, Luca.
Thank you.
So just a short recap. So we presented like how basically to access the data, read and write parts of it using the local data that we have in the virtual box, like in the machine, and some of the remote data also. So this is actually the first part. So to really read the points, read the raster data, and in the afternoon we will use these functions, but now in the context of spatial and spatial temporal machine learning. So all these functions that we present, it's mainly to implement these input and output operations, like deal with these GeoTIFF files. And I would like just to, in my last in my presentation, the first part of this morning. So here you can see that I didn't present it, but it's the same method that we use here to read these three images. You can use the same approach. You just need to change which are the file system, the file names, and with these file names, this function find files, it's like a utilitarian function of Eomap. It will sort all the files in the chronological way, because the file name, it's you have the date inside of it. So mainly this function organizes all the files in a chronological way, and you can read all these files using this raster, and it's fully optimized, so it reads in parallel. You can control how much threads you can use to read it, and you read here all the 84 images. So here for the NIR, like the infrared band of the Landsat, so this is a totally harmonized product, so you have it for the whole Europe, and you can read it, and here you have like a complete time series with 4 observations per each year. So we have 20 years, and here it's 21, because it's 2000 to 2020 multiplied by 4. And what it's interesting, so here it's just like a NumPy array with the last dimension, it's the time. So each part of this array, so it's like a data cube with each part of this last dimension, 1 date. But with this function here, you can see I'm just plotting like a time series, and I'm getting like a random pixel here, and you can see the time series value. So how for this specific pixel, this pixel, it's one position in this data cube structure, you can see how it is changing. So in the tomorrow in the cloud optimized GeoTIFF training session, we will do it, but with real data. So we can actually access this temporal response for NDVI data directly through the cloud. So it's here again, you are reading the data. It's just local data. It's just part of Europe because we prepared it specifically for the training sessions. But you can use the same approach with the same methods, and you can point this to like a real data that we are hosting in the cloud. And you can plot all this time series for NDVI in our example. And here you can compare. So this is actually the structure of the data. So you can compare it across different years. So this method here, it's just like a function to help plot the data using like the plotter, the plot raster that we saw here. And you can send like 2 years, and you can compare how the image looks like. So the 4 seasons across different years. And here it's just like an operation between these images. So it's a sort of reduction. So considering all this data cube, you can do multiple operations. And in this case, it's just like a median. You can use like maximum calculation, minimum. So basically it's a type of a reduction in this data structure. So you have like 2 dimensions for the space and 84 dimensions for time. Each of these dimensions are specific for 1 season and for 1 year. And you can derive multiple statistics about it. So for example, here this code, it actually calculates like the median value across all these images, across all these time series. You could have like the maximum value, the minimum value. So it's a easy way with the work with this data. And here it's just an optimized way to access it, but all the functions available in NumPy you have available also to process and to deal with this data, because we are creating this Eomap function just to provide some helpers and to optimize, for example, specific parts of workflow, but it's fully compatible with what we already have in Python, NumPy, scikit-learn, as you will see like this afternoon. So yeah, this is the last part of the presentation. And you can see it's possible also save the raster files, and you can open it in the QGIS. And it's a nice way because when you save a file, you need to, you are reading a data, put it in memory. So you have a NumPy array, you can process and do multiple operations, but to save it as image again, you need to set several parameters. What is the projection system, and what will be the like the data format and things like that. So this method save raster, it's actually used as profile one like base image and copy all these geospatial parameters for all these images separately. And you can save multiple files like that also. So yeah, it's mainly what we want to present this morning. It's more about what data we are processing, how we are reading and how we are writing, and how you can access it using Python. So it's a preparation for the afternoon, because in the afternoon we will use this data to do a proper like machine learning model and classify it. And this Landsat data, primarily we will classify it in different land cover class. So yeah, I don't know if you have some questions. So otherwise we can stop the session, have a lunch, and prepare for the afternoon. Sorry?
Yes, no,
Ah, okay. Okay, so let's go back here, and I think if we don't have like more questions, I think we could start with, yeah, I can execute it, and we can, because yeah, let's do it. Okay, so I will open mine. So I was rushing, but as we have time now, I would like to explain about this data set preparation. So it's a nice context for the machine learning model. So mainly what we are, this is mainly the data that we worked till now. So the Landsat R and the images. So you can see here, this is a nice publication about the data set, but mainly we are downloading it from University of Maryland, as I said, and we are getting all the, like this 16-day style. So for the whole world, this product provides like one integrated image every 16 days. And when I say integrated image, it put together all the 3 Landsat satellites that are available, like Landsat 5, 7, and 8. So it's a nice product. It's a harmonized product, which mix all these pixel values. And when you think that there are 3 satellites different getting data from the Earth surface, you of course you have different problems, and it's really challenge. It's really a challenge put all this data together. So this is a harmonized product. It's nice, but even considering it, you still have missed data and you still have like clouds. So what we are doing, we are getting this data, and we are organizing it for each season. And mainly we have the date intervals here. So for example, between March, 21 of March and 24 of June, we will have like several images, maybe 6, 7, it depends. In winter, of course, we will have less images because you have more problems with cloud. But it changes across all these seasons. But for this time frame, for these dates, you have like multiple images. Mainly what we are doing here is we remove all the clouds. So there is like a mask. There is an indication of which pixels are cloud, which pixels are not cloud. And we are using this mask to really remove and clean the data. But of course, if we remove the cloud, so this satellite, it's an optical satellite, so it doesn't see across the clouds. So you have a value, a gap there. So, and if you have a gap, if you have a missed data, a null data, it is a problem to multiple applications. So it's better. It's mandatory. Put some value there to use this image in this format. But if you think that, okay, maybe for this interval, I will have like missed data, I will have gaps. So there are 2 options here. You can expand this window. So imagine if I have like pixel values here, cloud here, I can expand my window. So I can get all the images available, I don't know, in 2020, for example. And maybe some of these images will have like pixel value. So it is not guaranteed that I will have like observations, because it's a combination of when the satellite pass and if we have clouds or not, what are the climate conditions, but you can expand it. But of course, if you expand it, you will have like a final image with pixels derived from different observations, and it could mess the data. So it's why really it's important to harmonize all these observations. So, but in the context of the project, we decided to use other approach. So mainly we kept these seasons, and we gap fill it using like different years and neighborhood seasons. So, and I didn't prepare the tutorial about it, but we have available in the official documentation. I will just show to you, but we in the Eomap documentation, and in the official documentation we have these tutorials. So, and here it's like it's an exercise of how we are implementing the gap filling. So this is actually the code that we run. So, and you can see here where is the original data and where we gap filled the observations. So mainly it used like a moving window to get observations from different seasons and from different years and fill the gaps. Of course, you need to be aware that you are introducing like a new observation there that, and in some applications it could introduce some problems. So imagine it like in a case of a deforestation, if you put like a gap filling, maybe you are not see a real deforestation because you are using like a value from the past, for example. But at some point we will see that, and because at some point the satellite will pass through this part of the Earth to that part of the Earth, and you will have like a real observation for surface, and you will see it. So it depends of the application, but here, as we are dealing with data to the past, so past data since 2000, we have like some observations up forward also. So what we are doing, we are just using like the median value from past observations and from future observations. So for example, to gap fill an image in 2010, we will use observations from 2012 and from 2008. Of course, we will have limitations in the end of the year, in the end of the time series, like 2021. So, and we are preparing like a publication to explain it, but for the context of the project and to produce like land cover maps to the past, this data, it's prepared to do it. And of course, we have 4 seasons, and maybe one of these seasons has actually observations without gap. In the most part of the case, that is the case actually. So maybe we are gap filling, for example, the winter image because there are too many clouds in this season, but the summer image we have observation. So and we are using all the seasons inside of 1 year to produce the land cover maps. So this problem will be minimized, and here you have other approaches. We did test 3 of it and 1 more that it's not implemented here. And here you can see this is more like a linear regression between all the available observations in the across time. But you can see that our approach here, it captures better the seasonality. And we see these spikes because we just have 4 observations per each year. But if you think that this data, it's a 30-meter data, so, and it was prepared for the whole Europe, so we removed all the clouds, and it's a nice time series, and it allows to develop several applications on top of it. And so let's go back. And we will use a lot this data. And so just to explain like the last part, we did it for 3 percentiles. So mainly inside of each season, imagine you could have like 4 observations, 3 observations. Maybe you have just 1 observation. It's the case for the winter in the most part of Europe. But we are calculating these 3 percentiles for all the seasons. So this approach. It's kind of it's a straightforward way to organize this different data availability in 3 ready-to-use images. So, for example, if you have like just 1 pixel, for sure these 3 percentiles will be the same. But if you have like on the Italy, for example, you have better observations and a better data availability, you have 3 different observations for these 3 percentiles, because you will combine all these pixels and you will produce it. So the output here, of course, it depends of the data availability, but it's a approach that allows us to generate this data and to prepare it for the machine learning. And the assumption here is when we train a machine learning, we will use points from the whole Europe. So we will have all these different situations. So we will have points with 3 values, constant values in the 3 percentiles inside 1 season. And we will have values with like multiple values for each, different values for these 3 percentiles. And the machine learning, the model will manage it. So that was the assumption here. But again, there are multiple ways to deal with that. We could use like just 1 image for the entire year. That's a way. I implemented it in the past. But here we really preferred to generate the seasons and gap fill it. And it was more like a methodological decision, but of course there are different strategies that could be implemented. The important part, and I'm repeating it because it's not these satellite images, they are not like, if you think in the Landsat data, in the Sentinel data as they are available now, they are not ready to use. You need to do a lot of processing and you need to download it, you need to remove the clouds, you need to do a lot of harmonization to use, for example, different observations from satellites. So, and there are like specific projects to do it. So here we are using one of these products that already implemented it, and we are building like a new kind of an additional product on top of it. And if you use directly the satellite images, so you have a lot of work, and probably during the machine learn modeling, you will have problems because this even, for example, from the same satellite, you can have like different interference, different like noise from the atmosphere effects and things like that. So if you are really focusing develop like models and use this data, it's important to have a clean data, harmonized and ready to use. Otherwise, you need to implement that. And that's the reason of why we are doing it, and we are putting all this data available. So to allow other people, other researchers and other organizations to develop applications on top of it. And of course, we are improving this product. So now we are generating a new version, a version 1.1. And it's still, this product, it's not perfect. You can see like some artifacts still, but we are really improving it during the year. So when we have the capacity to rerun it. So I will, as I'm talking about it, I will open like one RGB image here So we can use the data portal to see it on top of my tutorial. It's the easiest way to check these composites. And if we go here, so this is a public URL you can access. And this is the RGB data. And I will use the 0 opacity, and I will zoom in someplace. You can use this to, yeah, we can try to find. So yeah, this is nice. So, and we are here, and you can see this is not like a Google Earth image, because of course each pixel here has 30 by 30 meters. So if you zoom in, it will not shift for a better image, as we are, as Google Earth do. You have the Google, not here is the Bing map, but it's just to show the difference. But this image, it's really enough to do like several environmental applications. And so, but what I want to show to you here, this is the summer image. So it's the best mosaic that we have available because of the data availability. And this is the medium value. And here you are seeing actually 3 bands, like the red, green, and blue. And if you go back here, you can see like from all the years, you can see some change, and you can see still some artifacts. So there is like rest of like some noise, some artifacts, because of course this processing, it's not perfect. We are trying to minimize the number of artifacts, but sometimes there are problems in the cloud mask. So it's really difficult remove all these problems. But what it's important is we are really like creating a optimized workflow to do it and to update it. And for example, if we find a better way to identify the clouds, we can run it and we can process again, and using all this infrastructure that we are presenting here. So what is nice, so we are here in Wageningen, and this is Veenendaal. And if you see all these images, you can clearly see some of the urban area expansion here. And this is only possible to see because we have 1 image per year here. And for each year, we have 4 images actually. Here it's just the summer. But for Google Earth, you have this, for some areas you have multiple images, but it's not really, you can't do analysis with that. So with this data, as we presented today, you can load the data in the memory and you can process it. You can derive some statistics. You can calculate like NDVI index. And for the NDVI, we put it all, and now I will turn it. So if you look here for the NDVI, you have the 4 seasons, and I will turn on the opacity, and you can do the same thing and see how the NDVI changes. And as we know, this area expanded. So we had an urban expansion here, and the NDVI will change because in the 2000 and the early years, probably it was some kind of crop or pasture area, and later it was converted to urban area. So the vegetation index changed across it. And if you can check the values here, so you can clearly see how it's dropping it. And so probably in this specifically in this pixel, maybe the conversion occurred here. So, and again, this is a data that we prepared, and we can try to identify it here. Yeah, so you can see that considering 1 year to other year, I will stop it here. So yeah. You had an expansion. So we used this data and we produced it as I presented, but I will show it because it's a nice example. So we produced this land cover map. So we prepared the Landsat data, we harmonized it, we removed the clouds, we put it available, and we calculated this NDVI index, and on using this data, so it's not really raw data, it's an harmonized product, gap filled and ready to use, but it's just data, right? It's just like, we just have a spectral value, like a pixel value that represents some response of Earth's surface, but it's not, there is no like directly mean for this pixel. I don't know if it's an urban area, I don't know, for example, if it's a crop, if it's a pasture, and use this data we actually produce for all these years, reproduced like a land cover map, and we actually classify it using these spectral values. We classify it as, my internet here, it's not helping, let me see. Yeah, now I have it. So here it's like this is the result of the machine learning model. So you can see that this area were like it was a pasture, I think. And so what it's interesting here, if you look the image, you can identify it. But yeah, it's because we all the most part knows like what is an urban area. We can see that maybe we can see the building growing up across the landscape, but for a machine learning model and to produce like a product on top of it, we really need to train a model, we need to provide training samples, so there is a whole workflow on top of this data. And if you put here, so here you can have like, you can see all the land cover class and when it was converted to an urban area. So, and this is like the result of the land cover classification. We will do it on the afternoon, so we will produce something like this as output for specific for the tiles that we have, and using the same workflow. And you have other classes here, and yeah, it's a more like it's a advertisement, a way to try to stimulate you for the next sessions until the afternoon, and we will really process this data and produce one like derived product on top of this Landsat data. And you can use it for other applications also. So inside of the project, we are using this data to map where are the tree species, for example. You can use this data to identify, for example, to map the soil properties, and you can, there are several applications to build on it, but it's important to emphasize that depending of the scale, depending of the area of your interest, if you plan to do something like that for a whole country, for example. All this data preparation, all this data harmonization, it's hard working, and it's hard work, and we are providing it as service for different users and different organizations and possible applications. Okay, we have more questions, or any questions actually? Okay. Okay, it's about the difference between the NDVI. Why it's subtracting the previous year. So it's the first year. Yes, I think it's related with yours.
Yeah.
I can explain. Yep. Ah, okay, it's more related with the Python syntax.
Oh yeah. Okay.
Okay, so what I'm reading here is it looks to you like we're subtracting the last year from the first year, right? Because yeah, the Python syntax is because this means that we're not using the first year, we're using every year after the first, because the first year has the index 0 and the second one has the index 1, and then if you say 1 and then this, oh okay, you get it now, great. So was that it? Oh yeah, indexing from 1 is better, but yeah, Python inherits from a long line of working on limited hardware and all of that. So yeah, no problem.
Yeah. Yeah. Indexes start from 1. It's weird for me, but it's how R managed the thing. Okay, so more questions, or let's stop. And now I think it's time to the lunch. Okay. Thank you all, and see afternoon. We see each other in the afternoon.